Hi, I'm Sravya Yandamuri, and I'm a graduate student at Duke University. And I'm going to present communication-efficient BFT protocols using small trusted hardware to tolerate minority corruption. And this is work I did with Itai Abraham, Karthik Nayak, and Mike Reiter. So in this work, we're looking at Byzantine fault-tolerant consensus. And in consensus, you want all honest parties in the network to agree on the same value. And Byzantine parties can behave arbitrarily, so they won't necessarily follow the protocol. And when looking at consensus, we need to define what our network timing assumptions are. So one assumption is synchrony, which states that there's a finite time-bound delta, and the adversary can delay the delivery of any message by at most delta time. On the other hand, in partial synchrony and asynchrony, there's no known delta bound. So the DLS Lower Bound states that it's impossible to solve agreement under partial synchrony against a Byzantine adversary if 1/3 or more of your network is Byzantine. And to quickly show why this is the case, you can imagine if you have 3 parties in your network and one of your parties is Byzantine, they can lie and send different values to the other 2 parties. And the messages between the honest parties can be delayed by the adversary. So since the honest parties need to decide something eventually, you can actually get a safety violation. So there's a couple ways to increase the fault tolerance of such a protocol. One way is to just assume synchrony, so the messages between the honest parties wouldn't be delayed. On the other hand, you can actually use trusted hardware to not allow equivocation by the Byzantine adversary. So one way to do this is to have a trusted hardware that must sign the value that the party is sending, and it will only sign one value. So here we have that this Byzantine party wants to send 1 to A and 0 to C, but only one of those values can actually be signed by its hardware. So if 1 is signed by its hardware, 0 won't be, and C will detect B's equivocation. And this approach is the one that we want to use. The Dolev-Reischuk lower bound states that if there are F corruptions, any deterministic Byzantine broadcast protocol needs to send order n² messages. However, for state machine replication in a view-based world, there are recent protocols that have done much better than this, and one is the HotStuff protocol, which gets linear communication complexity per view. The goal of our work is to increase the fault tolerance of communication-efficient Byzantine fault-tolerant protocols from 1/3 to 1/2 faults while maintaining their communication complexity. In particular, we wanted to do this with HotStuff, which works in the partial synchrony setting and incurs linear communication complexity, and validated asynchronous Byzantine agreement, which works in asynchrony and incurs order n² communication complexity. And for the rest of this presentation, I'm just going to talk about our work on the HotStuff protocol. And now I want to talk about the type of hardware that we use in our paper. So this hardware is in a trusted platform module in the hardware of a user's computer. And it cannot be tampered with even by a malicious host operator. And it maintains a monotonic counter and a small amount of storage. The state that this hardware maintains is a public key and a private key, which are used to sign attestations, and the private key cannot be viewed or modified by the host. In addition, it maintains a counter, which is just a single monotonic counter that corresponds to the length of a log. So now I'll describe one of the functions that our trusted hardware implements to give you an idea of how it works. So say that you want to append a value D in your log. So you invoke the append function with the value D, and your log is currently in the state that it has 3 values appended to it. So first it increments the value of the counter and writes the value D into the new counter position. And it returns what's called a lookup attestation, which says that value D is appended in sequence number 4, and it's signed with the private key of the hardware. And the important thing to note here is that the value in a given position cannot be rewritten. So there's only one valid attestation from your hardware for a given position of the log. And Trink actually shows how using a small trusted hardware, which just consists of a counter and a small amount of storage, you can actually implement such functionality. So the main results of our work include HotStuff M, which is a partially synchronous Byzantine fault-tolerant state machine replication protocol that has linear communication complexity per view and withstands minority corruption with some epsilon slack, and we do this using trusted hardware. In addition, we present the VABA-M protocol, which is a validated asynchronous Byzantine agreement protocol, which has order n² communication complexity and also withstands minority corruption. And we, again, do this using trusted hardware. And now I just want to talk about some prior work, and in particular the attested append-only memory paper, or A2M. And in A2M, they show how using a small trusted hardware like what we just discussed, you can actually get the property of non-equivocation. And using this non-equivocation, you can increase the fault tolerance of Byzantine fault-tolerant protocols. And in particular, they present a version of PBFT that withstands minority corruption. So recall in the steady state of PBFT, parties send votes to all the other parties in the network. And once a party gets votes from more than 2/3 of the parties in the network, by a simple quorum intersection argument, you get safety. And in A2M, they show that if parties just send attestations along with these votes, then you can actually get the same quorum intersection argument and safety with minority corruptions. But note that this sort of approach requires order n² communication in the steady state, and it actually requires order n³ communication in view change, since you have to send all these attestations out. So now I want to talk about the steady state of the HotStuff protocol. So in the HotStuff protocol, in the steady state, there's a series of these broadcasts, and in each broadcast, the leader sends some value to all the parties, and the parties check on this value, the validity of the value, and then send a vote back to the leader. And the leader collects these votes, combines them into a signature, and then uses that as an input for the next broadcast. And so while this seems like 3 separate phases of broadcast, HotStuff showed that this can actually be pipelined such that each of these phases performs exactly the same task. And one of these phases is called provable broadcast. So the provable broadcast for 1/3 corruption proceeds as follows. The leader sends a value V along with a proof sigma for its validity. And upon receiving this, a party verifies the value using the proof. And if it all looks good, it sends a signature share back to the leader. And the leader combines these signature shares into a constant size proof sigma prime. And note that the leader gets only one sigma prime just by a simple quorum intersection argument. And this incurs linear communication complexity. And so observe that since these provable broadcasts are used in a cascading manner and the output of one provable broadcast is used as the input of the next provable broadcast, since sigma prime is constant size, we maintain linear communication complexity throughout the view. So in our work, we want to have provable broadcast with minority corruption. But observe that we can no longer use the same quorum intersection argument to ensure that the leader gets a sigma prime for only one value V. However, we can use the same approach that they used in A2M with PBFT, where we have each party send an attestation along with their signature share, and the leader collects this list of attestations from a majority of the network and uses it as a proof to show that only one value could get this proof. However, when you use this in a cascading manner, as how it is in HotStuff, this would actually increase the communication complexity of the next provable broadcast in that view, because the leader has to use the proof created here as the input to the next provable broadcast. So this approach incurs n² communication complexity. So what we wanted to do is find a way to have parties create these attestations and have attestations of a majority of the parties in the network verified without having to have any parties send out lists of order N attestations. We also didn't want parties to have to broadcast their attestations to all the other parties in the network. So we found that by using an expander graph where all the parties in the network are connected in a constant degree expander graph, each party can actually just verify the attestations of a constant number of parties prior to sending their signature share to the leader. So in particular, we need this expander graph to have certain properties. And the first property is what gives us safety. And it states that if epsilon n parties receive votes from a majority of their neighbors, a majority of the parties have voted. And for liveness, we need a property that states that a majority of the parties in the network are honest parties with an honest majority of neighbors. So those two properties actually give us what we need to transform the steady state to minority corruption. However, they don't ensure safety across views. And I want to just quickly go over one problem that illustrates the complexity of the HotStuff view change process. And in particular, in the view change process, each party needs to send the value that they last appended to their log to the leader. But each party could have last appended a value to their log, honestly, in a different view. So how does the leader know if these parties are sending actually the latest values from their logs? They could actually send stale attestations, in which case you lose certain safety properties. So how can we ensure that parties send the latest attestations in their logs when these attestations can be from different counter values? And to recap our results, we present HotStuff M, which is a partially synchronous Byzantine fault-tolerant state machine replication protocol with linear communication complexity per view and withstanding minority corruption with epsilon slack. We also present BABA M, which is the validated asynchronous Byzantine agreement protocol with n-squared communication complexity per view and withstanding minority corruption as well. Thank you.